For this afternoon's presentation on unstructured meshes, what we've attempted to do is actually give a coordinated presentation. So instead of talking about one package followed by talking about another package, we're going to try to follow the topic area and insert discussions of the specific packages with the individuals associated with those packages and or tools describing those. So we'll be going back and forth a little bit. And the team members you're going to see speaking will be coming from Argonne National Labs, Sandia National Labs, and RPI in terms of the actual individual speaking. This slide just gives you an indication of the team that is involved with the FASTMath unstructured mesh activities and developments. In terms of the presentation today, I'm going to introduce aspects of unstructured meshes and why we are working on them. Then we'll delve into some of the core tools and presenting some of the specific packages associated with them. We'll then talk a bit about dynamic load balancing methodologies, and then hit into the topic area of unstructured mesh integration with solvers, and then go a bit further on the construction of adaptive loops, methodologies where we combine these solvers with mesh generators, with mesh improvement techniques and error estimators to, if you will, provide solution reliability. And then talk about some specific tools that have been developed with respect to that. Right, so what are we referring to as unstructured meshes? It's a spatial discretization of the domain in which we have general connectivities of what can be topologically variable types of elements. So there's not a lot of structure to begin with. Why do we want to consider unstructured meshing methodologies? One of the reasons is that there are techniques to go automatically from design data, from computer-aided design data, from image data, from whatever, to high fidelity meshes representing those models in a fully automated sense. The personal perspective I take towards this is, you know, if I do a great job on doing the solution technique, but I still have to do mesh generation and get involved with that at all, any aspect of the generating the mesh, I've just introduced a terribly slow serial aspect into the entire workflow process, because I'm a hell of a lot slower than the computer making decisions or fooling around with setting mesh control parameters, et cetera. So we really want to strive to as automated a methodology as possible. They can provide highly effective solutions. They're easily can fit exactly to the geometry, and you can track interfaces explicitly if you wish. With these, they can deal with mesh anisotropy, so you can account for the anisotropy that you may have in physics behavior, such as boundary layers in fluids or whatever. And as I mentioned, it can be automated and easily adapted. What are the disadvantages? Well, their disadvantages are why we have a whole team of people working on unstructured meshing technologies, and that they are more complex to deal with. They have more complex data structures, they have more complex algorithms to deal with the data in any effective manner, particularly on parallel computers. However, they can provide the highest accuracy per degree of freedom if you're quite careful about how you do that. And you have to be careful about the mesh layout, you have to be careful about mesh shapes. Of course, these things are a function of the discretization methodology. Some methods are more sensitive to element shapes than others, and how you bring them all together, and then how you interact with the solvers, which we will touch on. They tend to work well when you can work with adaptive methods in which you are tracking and monitoring the solution and changing the mesh to adapt to the solution, to make the mesh find where you have the action, if you will, etc. The goal of the FASTMath unstructured mesh developments are really to provide component-based tools that take advantage of what unstructured meshes can bring to the table, and to provide those components to applications so that those developing analysis programs don't have to become mesh generation experts or mesh data structure experts, and can build on that. And we have a variety of methodologies, primarily through APIs, for supporting people developing these. And we do work directly with DOE applications. And in this process, also, these tools, we fill specific technical gaps, such as, well, how do you do mesh-to-mesh solution transfer in a totally general case for a multi-physics type of simulation, or during an adaptive simulation where it's a localized process, et cetera. So this slide, which I'm going to skip over, just gives you a feel for a variety of applications that the FASTMath unstructured meshing team has been involved with in terms of developing tools for and having those tools integrated with these analysis packages. In the majority of the cases that we're talking about, we have coupled with teams that already have started the development of an existing analysis capability, and they pick up our technologies, integrate them in at various levels, and we'll see a little bit of that as we go along. Right, so what is involved with this? What if we're providing these tools and capabilities? What are we talking about with the mesh infrastructure? Well, certainly between nodes we need a distributed mesh. So we have a concept of a partition model in which we can have the mesh broken into individual parts. We have methodologies for controlling the communications between the mesh, for being able to move the mesh between and change the partitions, because we're going to be adapting the mesh, need to do dynamic load balancing, things like read-only copies for typical operations to make them more efficient. So we have the infrastructures and data structures to support the parallel mesh, as well as the partitioning of that, services such as load balancing, solution transfer, mesh optimization. And there are two implementations of these which we will be presenting to you. So the mesh is partitioned into parts. You can think of this really as a hierarchy of a topological representation. That is, we have a geometric domain. That geometric domain can be understood in terms of a topology of entities, of regions, faces, and edges and vertices. Similarly with the mesh, and to an extent, although it's not as explicitly represented, so is the partition model in between them. The mesh migration is, as I mentioned, is necessary to support the fact that the mesh may be changing, or you may be simply repartitioning a given mesh for different needs of different steps in your simulation workflow. Right? And of course, performance issues deal with the controlling the communications, synchronizations, and load balancing. We do support within the implementations generalized ghosting methodologies in which you can say how many layers you want, what it is you want to have layers of, and what are the bridge entities for that based on topological entities. So I may want to ghost one layer of regions based on common faces, which is going to give me a different ghosting than if I do it based on the common vertices on the partition model boundary, right? So mesh generation, we're typically not writing the mesh generators, although sometimes we do specific aspects of that, but we all support the integration of those. So what do you want to be dealing with the mesh generators? Well, you've got to be able to deal with mesh generators can work with totally general domains. We are doing meshes that have approached 100 billion elements. You need high levels of automations on that. When you're adapting the mesh, how do you account for the a posteriori information to improve the mesh, be it discretization error control or element shape control or detection of the formation of contact, etc. Also accounting for the fixed or for curved geometries with either straight-sided elements or higher order elements. So we do support curved meshes as needed to properly represent the domain when you are using higher order methods to make sure you're not losing your convergence rate because you're not doing your geometry appropriately. And there are tools for optimizing the shapes of the elements as well as adapting them. And and all three functions do need to operate in parallel. Fields and solution transfers. So the fields are basically tensor types of information, be it scalars, vectors. Typically up to fourth order tensors are commonly used because material parameters are fourth order tensors. How are they associated with the mesh, and how do you describe their distributions as defined by the discretization technologies, et cetera. Right? So at this point, I'm going to turn it over to Vijay, who's going to describe one of the implementations, the Sigma implementation.
So Mark introduced the concepts of what we do in FASTMath arm of the mesh generation and unstructured mesh toolkits. So I'm going to talk about a specific implementation, which is called Sigma. Sigma stands for Scalable Interfaces for Geometry and Mesh-Based Applications. So that's the website over there. It's a component-based design. There are several libraries under Sigma. Each of them provides specific functionality. The CGM, which stands for Common Geometry Module, provides sort of a unified interface for accessing the underlying CAD model. So it could be in a variety of different formats. It could also handle a facet-based representation of a complex geometry. So it provides several interfaces and API to query the geometric modules and get relevant information so that we can use that for either mesh generation or doing geometry-based solvers, for example, like Monte Carlo applications. The second arm of the second component in Sigma is the mesh generation toolkit, which is called MeshKit. There are quite a few algorithms in MeshKit. And it also has interfaces to external mesh generation tools and libraries. So it can understand the geometry representation that's provided by CGM and then generate a mesh, an unstructured mesh, that resolves the curvatures, that resolves the geometric features that you care about in your physics. And MeshKit can also output this particular unstructured mesh in a variety of different formats. And MOAB is the unstructured mesh data structure that is part of Sigma and can handle parallel I/O. It can handle several different element types. It provides functionality to query connectivity, adjacencies, and several types of relational queries in your unstructured mesh. So apart from that, there are also several solver interfaces, either for doing a single physics application or for doing a couple multi-physics application. So one of them is the linkage to PETSI. So Louis introduced the DM object in PETSI earlier today. And so there is a specific implementation that we wrote that uses MOAB underneath as a unstructured mesh data structure, and it uses and it provides functionality to utilize the scalable solvers in PETSI. So you could write your discrete solver based on this infrastructure, and you could think of putting together several such individual physics solvers and running a couple multi-physics simulation. And one of the fundamental processes in that is, as Mark suggested, the spatial coupling. So how do you transfer the solution from one physics to another? So I'll kind of go over some of that in the couple of slides. There's also interfaces for parallel I/O and visualization with Visit or ParaView. So those are some of the applications in Sigma. So what I want to talk about here is the actual computational workflow. So this is one of the kind of general use case where you have a complex geometry. So the geometry is actually a real-world CAD model of the Advanced Test Reactor in Idaho National Lab. So you have a complex geometry, a lot of curvatures, a lot of fine features. So we run it through some mesh generation algorithm. We decide where we want high resolution, where we want low resolution. We generate an unstructured mesh, which is in the middle. And then you'll hook it up with your solver, run your problem of interest, whatever your physics may be. And then you find your solution, you dump it out do different type of analysis and visualize your results, right? So that's your computational workflow. And the idea is Sigma provides different components that can help you get through that workflow. So as I mentioned, CGM provides abstractions for the CAD models, and MeshKit is written in sort of a hierarchical design where you can mix and match different algorithms. So if you have a edge mesher or a quad mesher that you would like to try, you could kind of replace them in this graph-based design in MeshKit. So several external interfaces to mesh generation packages out there also. So if you have your favorite package, you could potentially use that with one of these adapters. So of course, the fundamental goal is to simplify your computational workflow, right? So I'm going to talk more specifically about Moab unstructured mesh package. So Moab is a array-based unstructured mesh data structure. So what that means is the entities and all the relational the data is actually stored contiguously in memory in arrays. So apart from supporting unstructured meshes, it can also support stencil-based computations or block structured computations. It's written, or we've done enough work to make it thread safe so that if you have a hybrid programming model that uses Moab underneath, it shouldn't cause any issues in terms of thread safety. There are also support for load balancing or mesh migration as needed for your applications. There are support for several discretization kernels and for uniform mesh refinement. So you could load up a coarse mesh along with the geometry, and you could perform uniform mesh refinement in memory, for example, to create a mesh hierarchy so that you could use like a geometric multigrid solver that could accelerate your solution procedures. So you could potentially use the CAD model if it's available so that the new vertices that are introduced in your refinement conform to the actual geometry. Or we also have methods or algorithms that provide sort of a surface reconstruction. So basically, utilize the patch surface on the boundary and reconstruct a higher order surface so that you reduce your geometric errors when you refine the mesh. For adaptive refinement, there's a lot of ongoing work. One research area is the conformal mesh refinement. For triangles and tetrahedral meshes, it's sort of pretty straightforward, but for quads and hexahedral meshes, it's non-trivial. It's sort of an open topic still for the conformal refinement. For non-conformal, there are several standard design patterns that you could apply, but then the solvers need to be a little more advanced in terms of managing the hanging nodes and the degrees of freedom associated with that, right? So what do I mean by conformal and non-conformal? If you haven't seen this before, so the first picture is the original mesh. The second one is the non-conformal refinement, where you have hanging nodes in between elements that don't have the right connectivities, while the third one is the actual conformal refinement. In this case, it's the hex refinement in the conformal pattern. There are also several infrastructures that Moab provides to simplify discretization kernels, and also provides geometric searches for points. This is especially useful if you want to do solution transfer between very disparate meshes, which can happen if you're doing couple metaphysics problems, right? So especially with the solver interfaces, the discretization kernels become quite useful so that you can build your own solver infrastructure. We also have several mesh smoothing algorithms. So if you have a bad quality mesh that you might have gotten as a result of adaptive refinement or maybe a bad mesh generation process, you could also run a lot of these smoothing algorithms to create better quality meshes. And of course, parallel I/O also becomes fundamentally important, especially when you're dealing with billions of elements in meshes, which result in gigabytes of data, right, in file. So I'm going to focus a little bit more on the solution transfer algorithm in Moab. So this is the algorithmic structure, and there are several operations that you need to you need to go forward with in order to find a solution that is conformal from a source mesh to a target mesh, right? So the green represents, let's say, a source or a donor physics, and the red represents where I want the solution from the original physics to be represented, right? So I need to transfer the solution from source mesh A to the target mesh B. So we actually start off with creating a KD tree data structure, which actually looks at the source points, the meshes in the source, the vertices in the source mesh, and it builds a tree data structure in parallel, which stores several bounding boxes that store what bounding boxes encompass certain elements in the mesh. And then the next stage is, once the target physics understands where it wants to evaluate certain solution data fields, for example, it could be quadrature points in your finite element simulation, right? So the target physics sends back and aggregates the requests to the source physics meshes. And so all of this data is aggregated through the crystal router data structure, which actually minimizes the communication by aggregating several requests and sending it to a particular processor. And once this request is received, you can actually do a local computation and find out the index of the element that contains a particular point in the source mesh. So this is sort of like a setup phase. Once you have this information, now you could query multiple different times using the exact same data structure where you want to evaluate your data. So during the interpolation phase, you could ask for, let's say, a linear interpolation of your data on the source mesh onto the target mesh. And since we have already deciphered the communication pattern in the point location phase, it's a one-to-one communication. So we do a local evaluation of the data, and then we just send it point to point. You can also apply several types of normalization conservation once we have this interpolation mechanism in place. So this is some sample scalability results that we did on BGQ Mira at Argonne. We were able to achieve about 60% strong scalability. This is so that's up to 500,000 cores. So the KD tree data structure scales quite well, except that if you look at the operation split in the timings here, the yellow represents the point location phase. The point location involves building up the actual indices and finding out the actual indices, and that takes an order n log n complexity with the KD tree data structure. So if you were to replace that with a different data structure, we could have a higher scalability for that phase. But for real-world problems, you would do the setup once, and you do the interpolation multiple times. So for example, if you have a time-dependent simulation, and assuming you have a static mesh, right? You would do the point location once, and for several transient steps, you're going to do multiple interpolations between the couple physics. So it kind of gets amortized over multiple iterations. So I'm going to switch it back over to Mark.
The second implementation is the referred to as PUMI, which is a parallel unstructured mesh infrastructure. It maintains a complete representation where we simply define a complete representation, and one in which you can get any adjacency in order one time. Not necessarily store anything in them all, and you definitely want to do that, but you can obtain them in order one time. It's an array-based implementation to reduce the memory patterns, memory use on that. And the parallel control supports the types of operations discussed earlier in that. The focus of the implementation on this has always been on the support of adaptive calculations on evolving geometry problems. So we have the mesh changing, the domain can be changing either due to shape change or fracturing or whatever causes that shape change. We use it in construction of parallel adaptive simulation loops, which we'll see more of in examples. But in those examples, we're using various mesh generation tools, some from commercial vendors such as from Symmetrics, as well as the mesh adaptation tools that have been developed as part of FASTMath, coupled with dynamic load balancing tools developed both at Sandia and mesh and partition improvement tools developed at RPI. And this has been used on up to 750,000 cores, 3.1 million processes on meshes with 92 billion elements. We have also been doing specific architecture aware to start dealing with the fact that we have either heterogeneous nodes or certainly many core nodes. This is some preliminary results. I'm actually not going to go over these this particular part of that. Cameron may comment on some of the architecture aware work that's ongoing now, and that we've moved to some additional capabilities in the panel later this evening, because this is one of the critical areas on moving forward. How are we going to be running on the next generation machines and dealing with those? This was one step along the way on that is combining threading and message passing within a structure in which we have these distributed meshes. But there'll be some more discussion on that. In terms of the mesh generation, as I've already mentioned, we want to be able to go from CAD representations or image data directly to meshes. These are simply some of the examples of that. The mesh generation procedures, one of the reasons we tend to use these tools from Symmetrics is that, in fact, the mesh generation can be run in parallel. We can generate multi-billion element meshes in a matter of minutes on a small, on like 256 cores, and it has been scaled up to 2,000 cores with good scalability. There's problems we're doing for IBM at this point where there's an awful lot of geometry. So in fact, not only is the mesh distributed in parallel, but so is the geometric model. We don't have a copy of the entire geometric model on every node anymore either, so that even that is scalable. Okay, in terms of the mesh modification for adaptivity, we want to be able to employ a set of general mesh modifications, if you will, a complete set of those, and complete is in quotes. But basically, you want to have as much flexibility in the mesh adaptation as you would have in fully automatic mesh generation, but you don't really want to generate the whole mesh from scratch each time when you're adapting. Now, the typical assumption on why you want to be able to apply these local mesh modifications is because of the savings of solution time, or the mesh generation time, excuse me. And that's true, you do save mesh generation time, but in fact, a much more critical aspect of that is that if you're doing the mesh adaptation with these local operations, you can do the solution transfer locally as you go along, and that is much more efficient and more accurate, leading to the fact that when you go back to the solver step with this new mesh, you don't have some of the startup problems you often have if you have to do general mesh-to-mesh transfer. And the specific tools we've developed do support fully anisotropic meshes. We do curved domains. You'll see examples of these later on. And as I mentioned, we can do this incremental solution transfer. This slide just indicates some of the basic operations. There's entity level operations, and what you find is if you just leave it to single entity level operations, you can't always get the things you want. You need to identify more specifically when you have situations such as a flat tetrahedron, and what type of flat tetrahedron. There's actually 3 different types. And then what is typically a compound operation to deal with those. And you find fairly quickly you're doing the equivalent of what a mesh generator does to begin with, including, as shown on the bottom, as I'm refining, I'm pulling things to the actual curved geometry of the CAD model. There's a parallel field structure that goes along with this to maintain relationships of the solution fields on the mesh, as the mesh is evolving and maintaining that information within the same set of array-based structures. The local solution transfer simply means that when I'm doing mesh modification, it's limited to a specific portion of the mesh. So when I do that operation, that is when I change and transfer the solution. If I'm doing a refinement, solution transfer is exact because it's a nested thing. If I'm doing a collapse or swap, I'm at least keeping things local, so when I want to do a conservation, satisfy a conservation requirement or something, I know in the very localized field that I need to do that within, I can do that more advantageously. The status of this is, I mentioned, we've done up to 3.1 million processes of mesh adaptation, not only for general tetrahedral meshes, but anisotropic meshes, including mixed meshes with boundary layers, as often used in fluid dynamics problems, as well as being able to deal with curved finite elements, higher order finite elements, because we are working with some codes that go up to sixth order types of finite elements on a regular basis. The next couple of slides are just some examples of where the infrastructure is being used. It's being used in a fusion code, which happens to be working with higher order finite elements because it is solving a fourth order set of partial differential equations. We represent the entire data structures for the solve, for everything but the actual solve process, which is then constructed directly, the matrices, PETSI matrices from the data structures. We're also doing this in a PIC code in which we're providing very specialized mesh generation capabilities that are field following for these magnetic flux fields, and have basically taken their mesh generation process, something that was exceedingly painful, down to something that's now automatic and in a matter of a few minutes just to set up the mesh control parameters for new reactor geometries, etc. I mentioned we do the higher order meshes. This is an electromagnetics code from SLAC in which they are dealing with curved finite elements, and we generate and adapt those meshes for them. Right? The last ingredient I'm going to talk about is now the dynamic load balancing. So in the dynamic load balancing, FASTMath has two tools. The primary tool is the Zoltan libraries, which is their Zoltan and Zoltan 2 libraries, which provide multiple dynamic partitioning algorithms and general control of partitions, objects, and weights, including architecture-aware capabilities, and an additional tool, Parmo, which is used to improve the partitions, directly accounting for mesh adjacencies for being able to satisfy the needs of specific applications. And I'll comment on that as we go along. So what do we mean by dynamic load balancing? On this slide along the top, we have we've initialized, there's an initial mesh. We partition and distribute the data. We do a computation on it. If it's an adaptive calculation, we then loop back through, change the mesh, repartition, redistribute the data based on decisions on changing the partitions, and continue that process throughout the incremental simulation. So this is just a comparison of dynamic partitioning, in which you really have to have a very tight coupling of the partitioner with the application, be it the mesh adaptation procedure or the actual solve procedure. And in an adaptive loop, we're carrying out dynamic load balancing many times. The Zoltan packages have a variety of tools. They have 3 different types of partitioning algorithms in them. There's geometric partitioning, of which there's 3 different algorithms. There's a recursive coordinate bisection and a recursive inertial bisection, and a more recently developed capability referred to as multi-jagged multi-section, which is a faster algorithm. The decisions here are based on geometries we'll see in a minute. There are space-filling curve methodologies, also implemented in there, as well as the graph-based partitioners, both in terms of standard graph partitioners and hypergraph partitioners. Right, so geometric partition, a few comments on that. These are determining the parts using geometric proximity information. So the classic aspects of this are recursive bisection. You cut the mesh in half the elements on one side, half on the other side, cut the halves in half, etc. Inertial bisection just says do that based on, determine a moment of inertia, if you will, your long direction cut across that. So you end up with more you square cuts, if you will. The multi-section algorithm goes through in a particular order to make this faster. The space-filling curves is also a geometrically based procedure that follows based on grabbing spatially close neighbor methodologies. So the advantage of these are they're fairly simple, and they can be fast and very inexpensive, and they can operate at very high core counts. Clearly, if I don't have connectivity information, I can't be using a topologically based one, because that's based on some definition of topology. So if I have just particles in space, then this is obviously a methodology you'd want to use. Disadvantages is they're indirect methods in terms of what you want to control. You want to control the load balance as well as minimize the communications, and there is no explicit consideration of the geometric aspects, of the communication aspects in that. The topologically based mesh generators try to balance the workload while minimizing data dependencies by looking at the dependencies in terms of graph edges and trying to cut the minimum number of edges when making partition boundaries. Right? So what you're going to partition becomes graph vertices, and then the dependencies are graph edges. You then use various types of graph algorithms, of which there's a number of different algorithms that have been integrated into the Zoltan as listed here, both serial and parallel ones. The advantages are they do typically produce higher quality partitions. The disadvantage is they can be more expensive, particularly on very high core counts. To speed things up and to improve quality, you can also consider doing hierarchic partitioning, in which you are going to account for the machine hierarchy in that. That is the fact that you have nodes communicating across a network. You then got on a node multiple cores, or a combination of cores and accelerators, GPUs, if you will. So this can be used to dramatically improve data locality, and has been applied on a number of applications. Some small applications showed here. The tool that I mentioned, this Parma tool, partitioning using mesh adjacencies, was driven by an observation that with the graph-based partitioners, we were distributing the elements to load balance those, but in fact, when we went into the solution procedures, that what's important is the distribution of the equations. So we could repartition based on the equations, but I could also account for that based on the mesh entities if I know what the degrees of freedom are associated with. So for example, in a linear finite element, degrees of freedom are associated with the mesh vertices. So I will improve the partitions by migrating around to improve the load balance of the vertices. If it's a second order elements, and it's vertices and mesh edges. And this has been used to support elements with meshes with billions of elements and on up to 1 million cores. Often the vertex imbalance with running a graph partitioner can be very high, and we can knock that down to a very small percentage, usually at the cost of sometimes needing to a slight increase in element imbalance, but that's usually well worth it. We often save 10–15% of the total solution time by running this, which is a very fast procedure to do on a partition mesh. Finally is an aspect of if you're doing mesh adaptation, you probably want to actually do predictive load balancing. That is, I have a mesh that I'm going to adapt. I want to repartition it before I actually carry out the adaptations, where I'm going to assign weights based on what the mesh adaptation procedure is telling me. So if an element's going to be refined from 1 element to 8 elements because all edges are going to will be split, I'm going to assign that element a weight of 8. If I've got elements that are going to be coarsened in a region that's going to be coarsened, I'll give weights less than 1. I'll repartition based on that, and then do the adaptation after I've repartitioned it and redistributed the mesh. Now one would think, well, I'm doing that for load balance. I'm actually doing that for straight survival requirements, because if I don't do that, what I'm going to have is very large imbalances in the amount of memory use on the mesh as it gets much bigger, because all the refinements in specific areas, and I blow away the memory on a specific node while other nodes are actually using less memory if I don't do predictive load balancing. The Sandia people have also been working on load balancing to ensure the ability of applications to maintain scalability by accounting for the architecture and the solution algorithms ongoing there. So these are just some examples of things, as well as the work with the Zoltan work and the Parma work. So these are a couple of examples showing that. Right? In Zoltan 2, the architecture-aware task placement, again, this is accounting for the fact that we need to deal with these heterogeneous systems and the hierarchies of solution techniques. Right? Okay, so with those core sets of tools, we want to start being able to integrate those with the solvers. So we need to efficiently integrate the infrastructure with unstructured analysis codes. And the key steps there, of course, are the element formation and then the solution of the system resulting from the element formations and assembly process. And there's 2 sets of specific activities there. VJ will first describe the discretization manager being developed for Moab, and I'll talk about some work that was done by Ken Jansen with PETSI and the pasta code.
So as I mentioned earlier, we wrote a DM-based Moab implementation. So this is part of PETSI. There is a lot of ongoing work which are in a separate fork, and we hope to merge that back into core PETSI soon. So what is the DM Moab object? Right? It's a specific implementation that provides the interfaces that are exposed by the DM object in PETSI. So the idea was to kind of create a unified interface that would provide support for multi-complement problems, whether your discretization is finite difference, finite element, or finite volume on both structured and unstructured meshes. So it uses the native Moab implementation underneath to handle all the structured and unstructured meshes. And it has a linkage to all the PETSI solvers that you could hook up if you're solving your physics PDE with whatever discretization technique that you care about. So what's the advantage here is that you kind of leverage the scalability of both the unstructured mesh package and the solvers in PETSI. There are several helper and utility methods where you could build meshes in memory for simple geometries, or you could load an unstructured mesh through Moab that you either generated previously through your favorite mesh generation package along with the geometry if you want to solve that. It also provides sort of an infrastructure where you can play with different types of assembly techniques, mesh traversal techniques, especially since Moab is array-based. It provides options for optimizations on how you want to do the finite element assembly of your operator. So it sort of provides a framework where you can play around with a lot of different options, especially with the PETSI command line infrastructure. So the design of DM Moab also follows very closely to the DMDA, which is the structured, and the DMplex unstructured implementations. So what that means is if you are familiar with one of these interfaces, hopefully it's not a big stretch to get started for you with DMOAB. There are specific implementations that provide optimizations for both strided and interleaved access to field components. So if you have a multi-component problem, it opens up several different interesting preconditioning strategies depending on how you block your components, and that is sort of driven through your physics scale. So if you have strongly coupled fields, you probably would like to block them together, and you could play those different variations with the DMOAB interface. The interface is also written to be sort of dimension independent. So once you write your code to work in, let's say, 1D and you debug it, it's not a big stretch to actually push it to a 3D implementation. Mostly this comes out of the discretization kernels that are exposed within DMOAB. Right now it's just linear Lagrange, finite element type operators, but it's not that hard to add more exotic type discretization strategies there. So you could define different type of field components. You could define how the different fields interact with each other in these multi-component problems. There are functionalities and algorithms that manage the degrees of freedom that you can associate with either the vertices or the elements or the faces, depending on what type of discretization that you choose to use. There is also options to reuse the memory that's already allocated in MOAB. So for example, if you define a field on all the vertices on the MOAB data structure, you could potentially reuse that contiguous memory that's defined in MOAB and create a PETSI vector out of that. So you could use that in either your residual computations or your solution in situ visualization or whatever else that you can think of, where you don't have to reallocate that memory. So the block filling is what actually controls the strided and interleaved axis that I mentioned before. So if you don't have a very dense coupling between your components in your multi-component problem, maybe you could define a sparse coupling data structure there. So this controls how the your operator allocation is actually specified in your MAD AIJ or MAD MPI AIJ in PETSI.
Okay, the PASTA code is a CFD code that for Navier-Stokes equations, full set of turbulence models, et cetera. And it was developed with its own very particularized and highly scalable parallel solver that works very well for those types of problems. In recent years, we've started to do extensions to this code to deal with certain multiphysics problems which provide more challenging to solve system matrices. So it's very advantageous to see if we can couple it with PETSI, because PETSI has a much broader set of preconditioners that allow us to attack some of these additional problems and methodologies in more detail, right? So this is just some indication of the types of scalability that was obtained with PASTA to begin with. Now, what we discovered when we linked it with PETSI initially is that the PETSI solvers would be fast once we had the matrix. The problem was the mismatch of data structures to begin with, and the assembly process became a bit of a bottleneck. So working with the PETSI developers, that was dramatically improved. They basically provided an improved assembly procedure, and now we get just as good a scaling with PETSI on many of the classes of problems as we do with the native capability, which demonstrated very good, strong scaling. Okay. So the next portion of the presentation, what I'm going to do is quickly describe work we've done now on taking these pieces, that is, these parallel mesh infrastructure capabilities, and constructing complete simulation workflows for adaptive calculations, right? So the users that we're working with, these various applications, be it a fusion application, accelerator applications, computational fluid flow application for wind energy or whatever, airplanes, etc. We want to be able to work with their analysis codes. So we really need this component-based approach. We need to have advanced methodologies for integrating the pieces together, and we have been able to successfully apply that by taking this infrastructure. So that's the image on the upper right there, the pieces of that. That is the fact that we have an understanding of the overall geometric domain that the problem is defined in terms of. There is then information on the mesh topology and its shape information for the mesh entities, the simulation fields, the partition control and dynamic load balancing, right? So we've got this distributed topology, et cetera, and then we can couple these together. So this is a rather unusual view of the process of carrying out adaptive analysis, where, if you will, you look at the lower left there, and the little box says mesh-based analysis is the entire analysis code, and the data structure in the middle takes up most of the things, but it's really the parallel infrastructure that deals with what is the actual problem definition, interaction with the mesh generation, mesh adaptation, solution transfer capabilities, and also ultimately with the visualization procedures. So with this type of infrastructure, we've been able to attack a variety of different applications. Now, because in most of these cases, that mesh-based analysis code is one that already exists, and many of them are initially developed under the assumptions that their interaction is on a fixed mesh and they get everything via files. We needed to deal with that issue, in that if I run adaptive loops and I do all my transfer via files, I'm going to introduce a substantial I/O bottleneck. Not only is it a bottleneck in general because of the slower speed of transfer, but I'm also relying on something that I'm sharing with all other applications using the machine, so it's very unreliable as to how much my hit's going to be on that bottleneck. So we really want to develop methodologies for in-memory transfer, if you will. And the sort of the obvious approach to that is to build directly off of the APIs. We've not described that. There'll be more description of the fact that these mesh infrastructures have very specific APIs for getting things like topological adjacencies, et cetera. That's one way to develop these interfaces, and to some extent is sort of the most advantageous way. But it is also, if you go up to an application person that has an analysis code and says, well, this is how you can start using these tools, they very quickly tell you where you can get off the boat and go take a swim, if you will. So we've also developed methodologies, Cameron has developed methodologies where we can effectively just replace their I/O routines with data streaming methodologies that very effectively do the data structure to data structure transfers, in doing that and introduce substantial efficiencies in that. I'm not going to go into details of these, how we do that, but very advantageous. So the next few slides, I'm going to just do very, very quickly. These are some examples. So I mentioned the PASTA code already. That has been integrated in. We use ParaView for visualization. The mesh generation is with this MeshSim software, and it's their adaptation on this particular application. The actual domain definitions are in Parasolid or GeoMSim, which is a representation that developed by the mesh generation people, but it's of the real geometry that actually runs on a Blue Gene queue. A lot of people say, well, I can't run my CAD system on on a massively parallel computer. A, it doesn't run on it, and B, if it did run on it, they charge me too much money. Well, so that's why these guys developed this thing called GeoSim. It runs on IBM Blue Gene Qs, and have geometric models on up to, I think, I don't know how many thousand cores, a full petaflop machine we've run it on. So it's, well, Cameron can tell you how many cores that is. I always forget. With the models that were originally from Parasolid types of models. So that's been applied to problems such as active flow control, where you really have very large scale changes, and that we've got these piezoelectric actuators that are about this big, and we're doing entire tails of aircraft, because in fact Boeing, based on simulations and testing, of course, that's been done eventually, is going to be using these on actual aircrafts. And these simulations where turbulent models run on them. It's also been used for active flow control, for multi-phase flow problems. In this particular case, using a level set. We're doing work now where we have explicit tracking of the interfaces. Another aerodynamics application, instead of a finite element code, a finite volume code. The Fun3D code from NASA has been integrated in with this same infrastructure to do various types of problems. In this case, it's a hypersonic vehicle in which we're doing adaptation with, you can't see them on there, but there's adapted boundary layers with elements of aspect ratios over greater than 1,000 to 1, right? For the SLAC people, there's ACE3P code that solves the electromagnetics problems. In this case, the models are ACES models, and the meshes either come from multiple sources, including Qubit and MeshSim, that have been supported on this in both Visit and Parasolid and Paraview for visualization. And in this case, we're using these curved finite elements, the higher order elements, and although the geometry on the outside doesn't look so bad, that lower left image gives you an indication there's lots of stuff on the inside that we have to deal with also. And this has been also coupled with a pick method where we adapt to where the particles are being tracked. They track just a small stream of them, and we're adapting to that. The final one I'll mention, and there are other ones, is work we were doing for IBM where we're addressing solid mechanics aspects of integrated circuit designs, in which the analysis code is the Albany code that's in the Trilinos toolkit, which is a very advantageous capability. Things we've applied it to so far are deep trenches and solder bumps and a couple other things. In these applications, in the PASTA application, even though that's a code that was developed at our place, it was originally developed with file I/O, so that uses the data streaming for integration, as we used also for the Fun3D. With the electromagnetics analysis, ACE3P, we use the data streaming for the initial input, but now we need to go with higher than quadratic geometry, finite elements geometries in that, and we'll be actually using a combination of the data streams plus the low-level APIs to support the specific aspects of evaluating element Jacobians back to the original geometry within that. Now the Albany code, on the other hand, is a more recent code, is designed more in a component-based type of methodology, and our interfaces to Albany are directly through the APIs to begin with. And the interface to that, and as I mentioned, we've applied those to a couple of different applications. And in fact, at this point, I'd like to turn over the mic to Mauro, who's going to describe Albany in a bit more detail, in that if you are looking to develop a high-performance application and don't want to start writing your finite element software from scratch, the Albany code is very advantageous code that you can pick up and start developing your capabilities in with that, and that'll be explained in more detail now.
Good afternoon. Yeah, so Albany is this is a finite element application code, and it's thought to solve for solving in an implicit fashion multiphysics applications. And today we'll focus on, in particular, on Felix, which is one of these applications done in Albany that's for Landais problems. So here is an overview of Albany, and in particular the Albany ecosystem. On the top row, you can see different applications. So from the ice sheet, there's the things that then we'll introduce later. And then quantum devices design and atmosphere and topological optimization. And then on the right, we have computational mechanics. And as a cross-cutting this application, you have several enabling technologies, in particular the solvers, so nonlinear solver for solving nonlinear problems, and the optimization capability for inverting or estimating some parameters. We have embedded UQ for uncertainty quantification, and of course the linear solvers, which are pretty good, that rely on Trilinos solvers. And then recently we are working on performance portability to be able to run Albany on different architectures, and of course mesh adaptivity, which is the theme of these slides. And this is another big picture of Albany from a rather slight different point of view. So and you can see that it's basically this architecture is based on agile components, and on the bottom you see the most fundamental ones. So you see the linear solvers and the assembly of finite elements. And these two pieces can rely on an extra layer of abstraction that's used for running on recent architecture and many cores. And this is based on Cocos, which is another package in Trilinos. And then you have nonlinear solvers for marching in time, and you also have analysis tools for, as I said, optimization and certain quantification. And on the other side, you have, of course, the discretization part. So, and in particular, Albany can use PUMI discretization capability and adaptation. And so Albany is really tries to glue all these different applications to give something that's very flexible and powerful. And you have a lot of analysis tool. So now we focus a bit on the Felix and the Landais code. And so Albany heavily relies on Trilinos toolkit, and Felix as well uses dozens of packages in Trilinos. In particular, we use Nox and local for the nonlinear solver. So Nox is for mostly for solving nonlinear equation with Newton methods, and local is for parameter continuation. And then we have all suite of linear solvers and preconditioner, in particular multi-level. And then we can do large-scale John-based optimization. The derivatives, so the Jacobians and the adjoints, are computed through automatic differentiation, in particular using the package Saccado. And then we have the embedded in-memory mesh adaptation that was described by Mark. And so this Felix code is also now part of the next generation DOE climate model called ACME. So there are a lot of code that is to couple Albany to other climate codes. And we can also link to Dakota for uncertainty quantification. So now we step back. So I introduced you the software, and we step back a bit and try to look at the physics of the ice sheet problem. On the top right, you see this diagram of a simplified ice sheet. And so the way it works in a simplified way is that at the center you have snow accumulation, and then the snow will become more compact and will become ice. And then the ice will flow towards the margins of the ice sheet, and it's driven by gravity. And some part of it will enter the ocean and then melt in the ocean. Part of it will melt before reaching the ocean. And in fact, so the ice is really a fluid, so might not be, maybe it's not obvious, but it really behaves like a fluid, like a shear thinning fluid, like similar like to a lava flow. And can be in a model with nonlinear Stokes equation with nonlinear geology. And so if you take this picture and you try to stretch it in the horizontal direction hundreds times, then you more or less get to the scale of a typical ice sheet, which is a very, very shallow geometry. And in fact, can be pretty thick, so you can be up to 3 kilometers thick, but then the horizontal extension is thousands of kilometers. So it's really a shallow geometry. And in the picture on the bottom right, what you see is a shelf, so it's even more shallow. And of course, when you solve this problem, you have to take in account this particular geometry, and you try to exploit it as well. And so in particular, the meshes for this ice sheet are done starting from a 2D mesh, which can be unstructured, and then it is extruded in the vertical direction. And the adaptation as well in this case is performed in a similar way. So you adapt the two-dimensional mesh, and then that mesh will be extruded, and then you solve the problem in the 3D mesh. And now I'll just describe a few challenges that we had to face for this ice sheet code. So first of all is the scalability, solvability. These are very huge problem, particularly Antarctic and the Greenland ice sheets. And so, as I said, there are peculiar in the sense that a very shallow geometry. So when you try to work on solver, you have to take in account that, because you can imagine that because of this shallow geometry, the mesh is really anisotropic. So you cannot just use some off-the-shelf preconditioner. In particular, in this case, we design a preconditioner. Ray Tuminaro is the guy that worked mostly on this, and which is based on first performing. It's a multi-grid preconditioner. So, you first perform a coarsening in the vertical direction, an aggressive coarsening, until you get to one layer, and then you apply a more standard multi-grid preconditioner to the 2D mesh, to the 2D layer. And then this proved to work pretty well. And in particular, we can see in this table, you can see a weak scalability, some weak scalability results. And so it's we are able to go from 2 million unknowns to 1 billion unknowns, and just by increases by 2 the time. So of course, perfect weak scalability would be the same time, but we think that increasing by 2 is pretty good in this case. This is another challenge, is that so you want to solve the ice sheet, you want to solve the ice sheet dynamics, but you need to know what's the current state of the ice sheet. And although you have a lot of observation from satellites about the ice sheet, you don't really know what happens at the bottom of the ice sheet. And even if you're able to drill some holes in a few locations, these are super sparse data, so that they don't give you much. And so so we need initial condition and boundary condition. And so we in order to estimate this condition, this field, we solve this with PD constraint optimization, and we try to match the observation of the surface velocity of the ice. And in this case, I'm showing you a reconstruction, an estimation on the basal friction, so the friction that's between the ice and the bed, and of course where this friction coefficient is higher, then the ice will be slower, and vice versa. So on the left you see the estimated field, on the right you see the observation target, which is our target in velocity, and in the middle the velocity that is being computed with that estimated field. And then we are also working on parallel portability this in recent years, and This is done relying on this COCOS package, which is a sort of abstraction library, which is at the lower level, so a level that's lower to the Albany implementation, and it allows to build and run Albany on different architectures and to get performance and portability. So these are this work is still going, and here are some results on. It's not strong scalability here. There's a type. There's a weak scalability, and we compare a serial run, an OpenMP run, and a run on NVIDIA GPU, and so you can see that if the number of elements on each node is large enough, then both the CUDA run, GPU run, and the serial run are faster than the serial one, much faster actually. And but there's still work to do to try to get and you see that the CUDA run at one point gets stagnated. I mean, doesn't improve anymore. So there's still work to be done there. So it's all about iSheet, and now we present you another problem, which is large deformation mechanics. In this case, you see suspension bracket, and the idea here is that you want to see what happens when you apply a load when you try to stretch this, and if you don't do adaptation in this case, you can see that when you apply your load, some of the elements becomes very, very stretched, and they can be flipped, and so you cannot really integrate them. You basically won't be able to run the simulation. Your code will break. But if you do mesh adaptation, then you're able to solve these. And in fact, you can see some results in the bottom picture. So this is particularly important because in other cases, we usually do mesh adaptation because we want to get more accuracy, or if you want, or we want to solve the to have a finer mesh only where we need it. But in this case, you really need to do mesh adaptation. Otherwise, you won't be able to solve the problem. And also now they're also working on this and try to add adjoint capabilities for goal-oriented error estimation. And the last problem solved in Albany that I want to talk about is about the mechanical failures in integrated circuits. And in this, here you have the applications that you have a silicon buffer, and you want to deposit a layer of metal on top of it. And this happens at high temperature, so you can imagine that when the material cools down, the metal and the silicon contract at different rates, so you can have very, very high stresses. And in fact, you have a lot of chips that needs to be thrown away because you have a structure failure. So it's interesting to try to simulate this numerically and try to see if there are ways to mitigate this issue. And this again is combining Albany with PUMI, and is solving a thermoelastic plastic and creep model. And I think this is another example where you can see that here adaptivity is very important because of this complex structure. So you really also in this problem you have large deformation. So you really need to have a mesh adaptivity. So I think we did this. I'm done.